Here's my take on what you just read on page 88. If you think back to the fruit fly example, and I have here the page from your book where the fruit fly example happens. If we wanted to figure out the rate at which the number of fruit flies was changing, we found the slope. What we really wanted to do was find the slope of the function. We don't know how to do that yet. So what we did is we found 2 points on the function, pretended that this was the function because I knew this point and this point. So pretend a little bit that my function is linear. I can find the slope of a line. So I've found the change in y divided by the change in x. Notice it's not really of the actual function. That's the actual function, and I found the slope of a line that contains 2 points. So a line that contains 2 points from a function is called a secant line. And you can see here, if you read through that example in your textbook, they said that what we found, the average rate of change, is actually the slope of a secant line. Compare that to what you remember about secants from geometry. So I just put this up because I know there's a picture of a circle here. In your geometry class, you talked about the secant to a circle being a line that contained 2 points of the circle. So what we read on page 88, it's really similar to what we did when we wanted to find average speed and then instantaneous speed. We started by taking 2 points on our function. You can imagine connecting those 2 points, we get what's called a secant line, and we can find the slope of a line if we know 2 points on it. Then we wanted to find instantaneous rate of change. We let those 2 points get closer and closer and closer and closer and closer and closer and closer together until my 2 points were the same point, 1 point. We're going to use that same process to talk about rates of change, instantaneous rate of change. We already used that method to find instantaneous speed, which is one kind of instantaneous rate of change. Now we're just going to apply that same process to finding rates of change of the number of fruit flies or the rate of change of the amount of water flowing into a tank, instead of just finding the rate of change of distance with respect to time. So what you read in your book is that if we could let those 2 points that we're choosing on the function get closer and closer and closer together until they were actually the same point we were just using twice, then we'd be using not a secant line, but a tangent line. If we could find the slope of the tangent line, we get the instantaneous rate of change. That was the biggest, most exciting contribution to calculus when we came up with a way to compute instantaneous rate of change. So I want you to imagine. It's hard to actually define what a tangent line to a curve is. It was pretty easy to define what a tangent to a circle is, but it takes a little more, a little more algebra magic to understand really what a tangent line to a curve is. But look at these 3 functions that are graphed here. These are all examples of tangent lines to curves at the big point that's drawn in. Notice I can't actually say, when you talk about the tangent line to a circle, you can say, well, it's the point that only touches the circle in one place. But look at this tangent line. That's not true necessarily for other kinds of tangent lines, because that tangent line touches the function twice. But we still want to understand, we can still have an understanding of what a tangent line is. So what I want you to notice is that if you were to zoom in on your calculator in any one of these pictures, it would seem like the tangent line and the function became the same function. You already have the experience of zooming in on a function and noticing that if you zoom in more and more, eventually, at least the functions we look at, they begin to look like they're linear. That's called local linearity, and it's an important idea for the rest of calculus. So I want you to imagine zooming in at that one point where the line is tangent to this curve. If you zoomed in, the curve would start to flatten out like a line, and it would be exactly the same as the tangent line. Turns out that's our best understanding of what a tangent line is. It's the line that touches a curve at a certain point, and it's the best match for the function at that point. Meaning if you zoomed in, that's the line that the curve would appear to flatten out into. So just to clarify, what we just said that it's the line that the curve would flatten out into if you would zoom in. That's what you're going to write in your best explanation for that up here in that circle. So now we're going to zoom down here. All right, so imagine this is what I'm going to do. I don't want to find the slope of a secant line. I want to find the exact slope of my curve. So I'm going to let my 2 points on the line, right now they're this and this, get closer and closer together. So before we do that, we want to write an expression for that slope. So here in this circle, I didn't give you much room, but what can we write for an expression for the slope of the secant line we have right now? So it's going to be change in y divided by change in x. So I see that if I go from point P to point Q, so think of the Q as your second point, so I'm going to have y2 minus y1. This is going to be f of a plus h. That's the y coordinate of the second point, minus the y coordinate of the first point, which is f of a, all divided by the change in the x's. So that's the second x, a plus h, minus the first x, that first x was a. So that says f of a plus h minus f of a, all divided by a plus h minus a. And you can see my note below. This is called the difference quotient. We're going to spend a lot of time this year working with difference quotients. Have you guessed why it's called a difference quotient? So you can see we have a quotient made out of two subtraction problems. So difference meaning subtraction. The result of subtracting the two y values divided by the result of subtracting the two x values. So a quotient made out of two subtraction problems. That's why we say difference quotient. So we already have this experience of trying to take 2 points on a graph, let them get closer and closer and closer together. That's what led into all of our discussion about limits, which we're going to be able to use here again as we work in section 2.4. So I have a note for you here. Let me see if I can clear out some of this stuff. So I've asked you to draw in 2 more secant lines. I'm going to draw one for you here, and then feel free to draw any 2 on your paper. So imagine if I'm going to let that point Q get a little bit closer. So I'm going to pick a point that's still on my function f, but it's closer to P than Q was. Now the secant line would be the line that contained P and I guess I should call that R. I'm going in order in the alphabet. So that's one new secant line. See if you can't fit in a second new secant line on your picture. Okay, so here's the big deal to come away with. If I have 2 points on the function, then the line that connects them is the secant line. And the slope of the secant line can help me, but it's really just an approximation of the actual slope of the function at that one point. So as I let h get closer and closer to 0, which means as I let the 2 points on the function get closer and closer and closer together until they're almost exactly, essentially, the same point, the slope of the secant line, which was an approximation, approaches the slope of the tangent line, which is the exact slope of the function at that point. So to be clear, that's in a big, fancy star because it's a super big idea. It's really critical for us. It's going to lead us into all of the rest of calculus. So before we spend a lot of time working with difference quotients and letting h approach 0, I want to talk about 2 important algebra ideas that come up. They're just sources of common errors, and I want you thinking about them before you do any work so you don't accidentally practice the error. So watch this. A very common error in calculus is to be working with a difference quotient and forget to distribute subtraction. So we're going to have lots of cases where I'm going to ask you to, for example, find the difference of 20 and 3x plus 20. Well, you know to write a subtraction problem when I say difference. The difference of 20 and 3x plus 20 is 20 minus, in parentheses, 3x plus 20. If you don't group that 3x plus 20, the part after the subtraction sign, in with parentheses, then that subtraction will not get distributed and you'll get the common incorrect result of negative 3x plus 40. But if I distribute here, I'm going to have 20 minus 3x minus 20. The difference is actually 3x. Second important reminder, if you're asked to raise a binomial or any polynomial to an exponent, to a power, you need to rewrite that as repeated multiplication. So if I have 4 minus x and I want to square it, I have to write 4 minus x times 4 minus x. If you actually do that in your head, that's fine. Just recall that it takes 4 multiplications. Please don't make the common error of saying 4 minus x squared is 16 plus x squared. It takes 4 multiplications. Don't forget that inside term.